Have you ever considered what it would take for a population's genetic makeup to remain just perfectly stable across countless generations, with no change whatsoever? This theoretical state of genetic constancy is elegantly described by the Hardy-Weinberg Equilibrium. It states that allele and genotype frequencies in a population will stay the same from generation to generation, but only if 5 critical conditions, or assumptions, are strictly met. These assumptions are vital because each one represents a force that can cause evolution. For the equilibrium to hold, there must be no new mutations introducing different gene forms into the population. There also needs to be absolutely no gene flow, meaning no migration of individuals into or out of the population, which would otherwise bring in or remove alleles. Mating must be completely random. Individuals cannot show any preference for specific traits or partners. Furthermore, the population size must be extremely large, ideally infinite, to prevent genetic drift, which is the random fluctuation of allele frequencies due to chance events, especially in smaller groups. Lastly, there must be no natural selection at play. All individuals must have an equal chance of survival and reproduction, regardless of their genetic traits. If any of these conditions are violated, evolution is occurring. Understanding these assumptions is crucial because the Hardy-Weinberg principle serves as a foundational null hypothesis in population genetics. It provides a benchmark against which real-world populations can be compared. When scientists observe deviations from Hardy-Weinberg equilibrium, they can then investigate which specific evolutionary forces, such as selection or drift, are acting upon the population. This framework allows researchers to quantify evolutionary changes and pinpoint their causes. By examining how real populations depart from this ideal, non-evolving state, we gain profound insights into the dynamic processes that drive biodiversity and adaptation across the globe.